Good morning, Fritz. I don't think he can respond, but I see Fritz Keilmann joining. So and he is of course the pioneer of everything we are doing.
Okay, we can start. Welcome everyone to this episode of MIDI, the MIDI Infrared Discussion webinar series. I'm Simone De Liberato, and together with Vincenzo Giannini, I'll be your host today. We are honored today to have with us Professor Dmitri Basov from Columbia University. Today, Professor Basov will discuss his works on Polaritons in van der Waals materials. Some practical information, the talk will be recorded and it will last roughly 45 minutes plus times for questions. If you want, you are also authorized to ask questions during the talk. In this case, either you raise your hand or you can write me in chat. I will unmute you and you will be allowed to ask your question. I think we are done, so I can leave the virtual floor to Professor Basov, please.
Okay, so let me start sharing my screen. Okay. So I think you should be able to see my screen now. Let me get the pointer.
Perfect, you are full screen.
Okay. Good afternoon, Southampton. Good evening, Singapore. I see some participants from Singapore, and it's beautiful morning here in New York. I will start by stating the obvious. I'm joining live from New York today. I'm really grateful for this invitation to participate in this series. This is a wonderful series. It's also a great resource since all talks are recorded, and I watched some of them, and they were extremely helpful. So this is very, very good. So today I will talk about recent results on Polaritons in van der Waals materials, and I will present the work that's being carried out in our center at Columbia that is focused on van der Waals materials. So this photograph may seem to you like another super spreaders event. Well, it's not. It has been taken just a couple of months before COVID. So back then we were just spreading viral ideas without any side effects. And this is a large group of people at Columbia and at the University of Washington that's interested in van der Waals materials and specifically in optics of van der Waals materials. And the results that I'm going to present is really a collaborative effort of a large group of my colleagues and collaborators in Washington, and also graduate students and postdocs at Columbia. And I would like to cover today two topics, two fairly recent works on Polaritons. One will be related to photonic crystals for nanolight. By nanolight, I mean plasma and polariton waves that can travel through on the surface of these structures, sometimes through the bulk of these structures. This will be backgated devices, and this will be more superlattices. So this will be one topic. My other topic is a new plasmonic platform that I think has extremely wonderful potential for mid-infrared and for visible and for terahertz. I know this series is focused on mid-infrared, but it's actually a platform that's operational across frequency ranges. And this platform comes from what we call charge transfer polaritons. Essentially, this is we implemented it. I will talk only about graphene, but we've done it for many other materials by now. And you basically put graphene on another van der Waals material, and you generate gigantic charge transfer between these two, and you create extremely high carrier density that prompt all these plasmonic features in graphene, and without need for gating, without need for chemical doping. And this creates some of the sharpest interfaces that I ever seen in plasmonic response. So we are extremely excited about the features, about the properties of this new platform that it's on the archive, soon will be published. And of course, nano-optical methods is going to be our tool throughout this talk. So all these plasmonic polaritonic observations are enabled by antenna-based nano-optics. This is a one-slide summary on or introduction to antenna-based nano-optics. This is a technique that's been under development for a number of years, and I noticed that Fritz Keilmann, who is really the pioneer of this technique, is joining our this talk today. Thank you, Fritz, for finding time to join us. The technique is a hybrid of a light source and of an atomic force microscope. And the basic idea is simple, and for that reason, it's extremely elegant. You collect light just from the area underneath your tip, and then you can raster scan your tip or your sample, and you get nanoscale maps of various forms of contrast that you want. This simplicity is perhaps deceptive, and it took years and years and many advances in developments that before this actually became practical. And now there are commercial instruments that enable this technology. In particular, Neospec, the company that started by Fritz and now is producing absolutely fabulous instruments for many applications. In our group, we added capabilities to this scanning probe microscopy that are essential for research in condensed matter physics. And if you are interested in condensed matter physics, you have to think of low temperatures, and that's what we added in our group. These ice cubes is a graphical representation of low temperatures, but I can assure you that there is no ice in our cryostats. In fact, that was a technical complexity, significant technical complexity to perform these type of imaging experiments in ultra high vacuum at low temperatures. And the other capability that we had actually jointly with first papers were jointly with Fritz. Martin Wagner was the key postdoc trained in Dresden, who joined our group and who introduced this type of measurements that allow us to perform experiments in pump probe mode with transient dynamics going down to tens of femtoseconds. I will not talk about ultra fast work, but I think all experiments that I'm going to describe today will require low temperatures. Polaritons are hybrid modes of light and matter. As such, this concept of polaritons is a unifying concept between quantum materials and quantum electrodynamics. And we had a brief chat before this talk with Simone on importance and general interest of strong coupling effects, but that will be outside of this presentation. But it's certainly in the realm of what we can investigate with nano-optical methods, and that's maybe one of the most exciting directions now. So, in today's presentation, Polaritons will be a tool. That will be a tool that enables novel means of inquiry into the physics of new materials, new quantum materials, of monolayer materials and of superlattices of these materials. So here's the key idea. So you can think of a polariton as of a ripple with electron density, if it's a plasma polariton that's triggered with light. And the key idea here is that polaritons are not static. They can travel. They can be launched by the tip, and they can be reflected by physical edges of crystals or electronic boundaries in the interior of our crystals. And then you form very complex but interesting and telling profiles of contrast on the surface of your samples. And from these profiles, you can learn physics. So that brings us to a very different and new style of optical spectroscopy, we think. Conventional optical spectroscopy is all about colors. We study how much light of a given color is reflected, transmitted, absorbed, emitted. Here, with the help of polaritons, it all is suddenly about shapes. It's about shapes of the standing waves that we can form and that we can visualize with the tip. There is an analog in condensed matter physics in tunneling experiments. Our tunneling friends like to study quasi-particle interference on the surface of samples. And then from this interference profiles, they learn about electronic phenomena in materials. We are doing kind of the same thing, except for the interference pattern is produced by nanolight, by these polaritonic waves, and this enables entirely new observations that are not possible with conventional spectroscopies. This brings us into an entirely new parameter space of measurements and finite momenta, first of all. So this is very useful, we think. So this is a quick introduction to visualizing polaritons and polaritonic imaging. A key idea is not particularly new idea. It's an idea that an interface between a medium with negative dielectric function and positive dielectric function can support a propagating wave traveling along the surface. Graphene, with its high density of Dirac quasi-particles, is a wonderful plasmonic medium. This wonderful source of negative dielectric function that's a prerequisite for the formation of these surface waves. And the whole physics of this is really contained in the dispersion of plasmonic plasma polaritons. So dispersion starts very close to the photon line, so it's small omega and k polaritons, plasma polaritons are not that different from free space light. But then the dispersion bends to the right of the photon line. So that means that at a given frequency, you have modes with much higher momenta, and that means that you have confined waves on the surface of your plasmonic medium in graphene. This confinement could be as high as 3 orders of magnitude. I think the record confinement has been demonstrated by Rainer Hillenbrand and Frank Coppins in some of their experiments, first in terahertz, and now in mid-infrared. There are also extremely confined modes that have been recently observed. So there are several reviews on the topic. There is one review that I wrote with Misha Fogler and Javier Garcia de Abajo, and there's another companion review written by Tony Lowe and many other people whose names are familiar to you. Over the COVID lockdown, together with my colleagues at Columbia, we've written another review just on polaritons, and even a subset of this literature has produced 564 references in this review. It soon will be published. So it's an enormous topic and very rapidly developing topic, and there are so many interesting things happening. So now, how do we learn physics from polaritonic waves? That's fairly straightforward. And the point is that the response function of a material, for example, the complex conductivity, that's in general not only frequency but also momentum dependent, this response function is encoded in this dispersion. It fully defines this dispersion, okay? And that's a very important part, because in any optical experiment, your starting point is to evaluate the response function, because that's how the quantitative analysis of all data starts. And it turns out that you can experimentally extract this dispersion from imaging polaritonic waves in your systems. Okay, so if you do this nanoscale imaging experiment to record these waves, you can reconstruct the dispersion, as I will illustrate in my next slide, and that basically completes this loop. So the dispersion is experimentally accessible, and so it allows you, once you have that, you can extract the response function. In other optical experiments, you learn about response function from fairly complicated analysis that often involves Kramers-Kronig relationship, when you have to obtain your optical constants over very broad frequency ranges, or you need to use ellipsometry, or you need to use other things. Here, it's at least conceptually, it's a very appealing proposition. You do measurements with monochromatic light, you determine this, you extract these plasmonic waves, and you end up with a response function that's not only frequency, but also momentum dependent, something that you certainly miss in conventional optical experiments. So if you want to learn about the response function of Dirac electrons in graphene, then plasma and polaritons are your friends. Van der Waals materials support many other forms of polaritons, and we talked to Simone about phonon polaritons that are extremely interesting in this class of materials. Maybe, I don't know which ones are more interesting, but but they really enable very unexpected, non-intuitive optical effects, like propagation of polaritonic waves in the form of rays inside of crystals. So if you want to learn about lattice dynamics, these phonon polaritons are your friends. If you want to learn about semiconductor physics, then accident polaritons is another certainly very accessible class of phenomena from this type of experiments. My favorite polaritons are Cooper pair plasma polaritons. I like them because they are lossless. So that's actually both on the physics side and on application side. The major problem with polaritons is losses, but here the negative dielectric function is formed by superconducting condensates. And these Cooper pairs, we know that even in dirty superconductors can travel without losses for miles, or maybe even longer. And so polaritons formed by these Cooper pairs are also expected to be to show these very special lossless characteristics. For completeness, I will mention magnetic polaritons. So these three types, plasma polaritons, phonon polaritons, and accident polaritons, have been visualized, and I think we've made as a community, we've made very good progress in recent years in understanding the physics of these, because imaging became possible. These other kinds, these magnetic polaritons and plasma polaritons, are yet to be investigated in some details. So how do we visualize this? We start by selecting the frequency of our lasers in the range, interesting range of the dispersion. So then the tip of the near field apparatus starts launching plasmonic waves, spreading them in all directions. The wavelength of these waves is solely determined by the dispersion. The role of the tip in this experiment is to convert free space light, is essentially zero momentum light, into high momentum Polaritonic wave that can only travel on the surface. And you can catch this wave with another tip. That's doable, but not very practical. If that's what you want to do, then with this second tip, you can outcouple this plasmonic wave and send light to the detector. But starting from 2012, we've been doing something slightly different, and that has been done first in parallel with Frank Coppins and Rainer Hillenbrand. What we do, we form a standing wave on the surface of the crystal between the tip and, say, the physical boundary of the crystal. And then you launch this wave with the tip, and then you catch this wave with the same tip, and you use the same tip to outcouple Polaritonic wave and send light to the detector. And so when you do your scanning experiment, then you basically go through a series of these observations. So these are raw data. This is not just a pretty picture. These are raw data. Here is the physical edge of the crystal, of graphene crystal. And you see that plasmonic waves are strongest close to the sample boundary and then decay as we move into the interior. But they still can travel over very, very long distances at low temperatures. So that was the key novelty of this particular experiment, that has been conducted at low temperature when phonon dissipation is eliminated, and plasmonic waves still compact but can travel over very, very, very long distances. So how do we extract the dispersion? Well, we read the wavelength of Polaritonic waves directly from raw data. That determines our location on the momentum axis. We know at what frequency this experiment has been done, and so at the intersection you get one data point, and then you can repeat that at a different frequency of your laser source, and you get another data point. So it's a pretty slow process, a tedious process. Even in PowerPoint it's slow, but in real life it's much slower. So what we do often, but not always, often we now put an extended frequency source here, and so we then do Fourier transform spectroscopy on this scattered light, and that allows us to extract an extended segment of the dispersion, if not the entire dispersion, then at least extended segment of the dispersion in one shot. Okay. So please feel free to ask questions anytime. So I'm done with sort of introductory part. I'll now switch to charge transfer polaritons that we recently discovered in graphene on ruthenium chloride. Please feel free to ask questions anytime. It's difficult for me to read the chat, but maybe Simone could kindly agree to read questions. Okay, charge transfer plasma polaritons. Here is the story. And I would like, from the start, I would like to acknowledge numerous discussions with Eric Henriksen and also Ken Burge on this subject. And in fact, it was an article by Eric Henriksen, who the article that prompted sort of our work in this direction. Last year, he has reported transport measurements on graphene ruthenium chloride heterostructures. And from his transport experiments, he observed a substantial carrier density in graphene layers when they're placed on ruthenium chloride. Ruthenium chloride is another van der Waals material, exfoliatable material that you can exfoliate down to single atomic layer or few atomic layers. So it offers very flat surfaces and very good sort of mechanical contact, if you wish, and promoting interaction between other van der Waals layers. So graphene was the immediate choice. The work functions of graphene and of ruthenium fluoride are drastically different. And what Eric wrote in his very important paper is that he proposed a mechanism that for this high carrier density in terms of charge transfer of electrons from graphene layer to a ruthenium fluoride layer. So this charge transfer process leaves a hole behind, and this hole may prompt electronic response. This conjecture was supported by transport experiments in the group of Klaus Kern and now in several other groups. And very important piece of work comes from the group of Valenti in Frankfurt. She and her group calculated the band structure dispersion of this interface and concluded that graphene indeed may become extremely heavily doped as the result of this charge transfer process. So our idea for this experiment was to try to quantify the degree of charge transfer. We wanted to measure the Fermi energy in graphene as the result of this process, and we were hoping to do that by observing plasmonic and polaritonic waves. So the physics is sort of straightforward by now. We through a decade of plasmonic imaging experiments that we've started in parallel with Frank Coppens and Rainer Hillenbrand, we know that the plasmonic wavelength is uniquely determined by carrier density in graphene, and carrier density in graphene is uniquely determined by the Fermi energy. So if you measure plasmonic dispersion, you can read the Fermi energy in graphene layer from this nano-optical observation. So that's the idea of the experiment, and these are the raw data. So this is the structure schematic of a structure that Björk Jassen has made. It's actually one of the simplest structures that we ever investigated, because there are no contacts, there are no backgates, no nothing. It's just really a graphene layer sitting on top of this ruthenium fluoride. And if the hypothesis of charge transfer is correct, then we would expect to see plasma polaritons. That's what we see here. So these are raw data. Dashed line shows the physical boundary of graphene sheet. And if we move into the interior, away from this edge, we see periodic oscillations in form of these parallel lines to the graphene edge. We also see these circular regions inside of our crystals. So we think we understand that actually very well. So all of these circular plasmonic features are related, are anchored to defects in our structures. So if graphene layer ripples a little bit over ruthenium fluoride, then the charge transfer process is no longer that strong, and so we end up with a region of graphene that's free from free carriers, and so these regions are not conducting, and they act as reflectors of plasmons. It's a very important idea, actually. So plasmons can reflect from the physical boundary, but plasmons can also reflect from electronic boundary, from regions of undoped or ungated graphene. We've demonstrated that in the past, and that's what we observe here. And then there is a third type of plasmons, these so-called edge plasmons. These are plasmons propagating along the physical edge of graphene layer. So you see a series of dark and bright spots along the edge. So all three types of plasmons are actually well studied in separate samples in different situations, well understood. And these three types of plasmons give us complementary results for the Fermi energy and for carrier density in graphene layer, and that's how we extracted the Fermi energy of about 0.6 electron volts from these three complementary plasmonic observations. This is a very high Fermi energy. It's very difficult to achieve this Fermi energy with electrostatic gating, but graphene and ruthenium fluoride, this charge transfer process immediately gives you this high density. Dan Rieser, who is the key experimentalist in this work, he's a postdoc at Columbia. He has performed these measurements also as a function of temperature using our home-built cryogenic nano imaging system. So these are head-to-head comparisons of data at ambient and at low temperature. You see that plasmons at low temperature are much more pronounced. You see many more of these oscillations. The wavelength of these oscillations remains roughly unchanged, meaning that the charge transfer process is temperature independent, but the damping is very temperature dependent. And essentially you see more of these plasmonic lines because you turn off scattering on optical phonons or graphene. So Dan has performed very detailed studies of the dispersion of plasmonic waves here. So I told you that this is a tedious experiment to do the dispersion one by one, but he was motivated to do it. And he has performed these experiments using many different lines of our tunable lasers. So you see that this dispersion is not exactly square root. So, and in fact, there are several branches in this dispersion. This is all understood by now very well. These additional branches come from, originate from lattice dynamics and boron nitride. Boron nitride supports phonon polaritons, as I already mentioned. Boron nitride is essential for these structures because it serves as a capping layer that preserves graphene in its pristine form. But it also possesses phonon polaritons, and there is a hybridization between phonon polaritons and boron nitride and plasmons and graphene that leads to these interesting features of the dispersion that are all here. So Dan has been able to study this dispersion in great details. The one reason why he was he spent so much time on the analysis of this dispersion is the following. So this charge transfer process, this process leaves a hole in graphene layer, but it also introduces an electron in the underlying ruthenium fluoride layer. And we were very interested in trying to explore what happens to these electrons. Ruthenium fluoride is actually an incredibly interesting material. It's one of the leading candidates for so-called quantum spin liquid materials, so that show unusual spin arrangements in their ground state. And there is an old hypothesis by Phil Anderson that quantum spin liquids actually become high temperature superconductors if you manage to introduce a high density of carriers in them. And the ruthenium chloride has been looked from that point of view. And unfortunately, it's almost impossible to introduce this high carrier density by gating or chemical doping. It's a material that doesn't want to be doped for one reason or another. But charge transfer process that we investigated, that Dan Rieser investigated in great details here, actually does introduce electrons in ruthenium fluoride. And this high density of electrons in proximal layer to graphene actually produces noticeable features in this dispersion. If you look with the magnifying glass at this dispersion, you start seeing this. We are not claiming yet that ruthenium fluoride is fully conducting. For that, we need to extend these type of experiments in terahertz range, where conductivity due to ruthenium fluoride will become obvious. But there are all hints of additional electronic response due to ruthenium fluoride in these charge transfer structures. Okay, so now I would like to move to any questions from the audience through the chat.
I remind the audience, if you want to ask questions, either you can write them in chat or raise your hand. We have a question from Alexander Dubrovnik. Is the charge transfer mechanism limited to monolayer or may appear for multi-layer graphene?
Thank you, Alexander. So it's not limited to monolayer. Bilayers also work. Under Waals, so bilayers is of course bilayer seems simple, but it's electrostatically it's a fairly complex system. So the two sublayers of bilayer actually carry different doping level behind the process of studying that. But even more remarkably, this works for many other van der Waals materials, and that's we believe it's a really the strength of this method that you can try many other van der Waals materials, put them on ruthenium fluoride, and bingo, you have plasmons that are so hard to sometimes to achieve with gating or chemistry. Thank you for this question.
We have a second question from Andrea Mancini. Can you briefly comment on how do you obtain the Polariton dispersion when using a broadband source instead of sweeping a narrowband laser?
While the fundamental principle is Fourier transform spectroscopy. So if you have an extended source and you put a Michelson interferometer and you send light, backscattered light from the tip into Michelson interferometer that has been pioneered, by the way, by Fritz Keilmann as well. So then this Fourier transform approach gives you a broadband band spectrum. But then there is a real space aspect to that as well. And so these plasmonic waves have different periodicity at different frequencies. So if you now imagine for a moment that my frequency axis is, my horizontal axis is frequency and not coordinate, then you'll see that all these dispersion lines will start fanning out. And we've done that. We published quite a few papers on this approach of probing the dispersion. But the key thing is that you can extract all frequencies, information at all frequencies at once with the help of Fourier transform Michelson interferometry.
Okay. Next question from Michele Ortolani. What is the role of curvature radius of the tip apex in deconvolving the Q-dependent information?
Thank you, Michele. So the curvature of the tip, roughly what it does for you, it gives you the range of momenta over which you have some information. So it's imagine a bell-shaped function on the momentum axis that's peaked at 1 over tip radius, but it starts at 0 and extends maybe to 3 times the peak. So that's where. So if you have a very coarse peak, you don't have this coarse tip, you don't have this information. If you have very sharp tip, you shift your your bell-shaped curve to higher momenta. So it's not a tuning knob because you don't select a single K with a tip. You always have a range of tips Ks. But playing with the tip radius and with the frequency of your light source, you can get the full dispersion.
Next question from Rocco Citroni. Can you study also be applied to energy harvesting?
Applied to
energy harvesting.
Energy harvesting. Well, yes, and that has been done. So with energy harvesting, you want to understand optical phenomena in your materials. So many depending on what's your favorite approach on energy harvesting, then you can maybe work with multi-layer structures, or maybe you work with granular structures where you have this interesting charge transfer phenomena between grains. So in either case, all physics is local, spatially local. So you really want to have an nano-optics probe to understand what's happening in your device at relevant length scales, and you should buy a near-spec microscope for that.
Then we have a question or a comment from Alexander Goviadinov. Perhaps I missed it, but why do you not see any polariton in the middle branch, 1100 to 1300 centimeters -1?
I think we haven't looked at them very carefully. So also this middle branch is where you have excessive damping in this type of structures. So we haven't looked at it in great details. But these branches that have carry most of the dynamic range, that's what was important for us, to get the full dynamic range, as broad dynamic range in this polariton dispersion as possible, because through that we were extracting quantitative data on the conductivity not only of graphene but also of ruthenium fluoride. And so we passed on this branch for that reason.
Next question from Bill Barnes from Exeter. Lovely stuff, nice talk. Do you think this approach would work to explore vibrational polaritons in, say, a polymer film, molecular vibration hybridized with the surface plasmon of an underlying metal film?
So, not only it can be done, but it has been done. So, and I would like to refer to extremely interesting papers from Rainer Hillenbrand's group, precisely on this topic of polymer coupling to vibrational modes of some of the van der Waals materials, and to reach a strong coupling regime between vibrational modes in these organic polymer semiconductors, and in that case phonon polaritons in boron nitride, but physics of plasmons in that aspect is quite similar, and can be looked at as well. Yeah.
I think we are done with the questions for the moment.
I really appreciate questions. Thank you. I'd like to thank the audience for questions. So, okay, let's see. It has been 45 minutes, Simone. So
we have normally we don't include questions, so please feel free to continue.
Okay, because I was told.
If you have other material, otherwise.
No, I have material for several of these, but but it's. I was always taught that it's a criminal offense for a speaker to run over time. So that's So I'm always trying to be on time.
Well, normally we try to finish within 1 hour, including questions. So we have 15 minutes left.
So we'll talk about photonic crystal for nanolight, for plasma polaritons, and I will tell you about one or maybe two platforms for controlling propagation of plasma polaritons in van der Waals structures. Both of these platforms can be traced back to the idea of a photonic crystal. Basically, you implement a certain pattern of periodic reflectors in your structure, and then you force plasma polaritons to travel in the environment of these reflectors. And as these plasmonic waves travel, they encounter regions of different conductivity. This could be conducting channels in Moiré superlattices, or this could be regions of different carrier density in these gated structures. And these periodic reflectors modify the dispersion of plasma polaritons. Specifically, they introduce these gaps in the dispersions in the conventional square root of Q dispersion. You introduce a gap, just like in photonic crystal, but you do it for polaritons. On the left, you see a platform that's basically a backgated structure. That's the difference from a common backgated structure is that the gate insulator is shaped in the form of pillars. So you have very different carrier density on top of the pillar and in between pillars, okay? And then you can have any pattern you want, any pattern you can achieve with lithography, and then you can force your plasmonic wave to travel in this environment, and you get gaps in the plasmonic dispersion from that. On the right-hand side, it's a different type of photonic crystal. So this is a twisted pair of layers of graphene at a very small layer. So they form more as superlattice. And you see an image here reveals the contrast due to domain walls in this Moiré superlattice. And these domain walls have high conductivity. So for plasma polaritons, they also act as reflectors. And you get all the profiles with interesting patterns and gaps and control of plasma polariton propagation through this. So I'll start with photonic crystal in gapped structures. So this is sort of a device that we study that's been deconstructed in this image. So we have pillars of SiO2 in this structure that we will use as a gate insulator that produces non-uniform carrier density in the graphene layer. Graphene layer is continuous, and that's actually the common property of both of these platforms. You have a photonic crystal here, but you implement this photonic crystal in a continuous media. You don't drill holes, you don't cut cavities in your graphene layers. Graphene layers are still continuous in both cases, but you modify the dielectric environment or electronic structure, and you achieve photonic crystal functionality out of it. Okay, so with backgated structures, what we wanted to achieve is this photonic crystal character in a continuous plane of graphene, and so we wanted plasma polaritons to propagate over long distances. So we want to keep graphene layer in pristine condition. So we encapsulated it with boron nitride. And we also performed experiments at low temperatures when phonon scattering is turned off and plasma polaritons can travel over long distances. We are not, we are testing device capabilities, I guess, here. So obviously, for anything practical, you need room temperature operation. But as a start, low temperatures were extremely helpful. And then we assemble the structures and we apply gate voltage. And when we apply gate voltage, we get a profile of carrier density, low carrier density in between pillars and very high carrier density at the pillars. Because we basically at liberty to produce any pattern we want, we decided to be a little adventurous with these patterns, and we introduced a domain wall between these two hexagonal motifs, which just by shifting one with respect to each other, you create a domain wall that has very different plasmonic properties. So this is work of Lindsay on in our group, and the structures were prepared in the group of Corey Dean, my colleague at Columbia, and what was essential for all of these structures design is numerous simulations that we have carried out. This would not have been possible without Gennady Shvets. Again, it's conceptually very simple, but the devil is in details. And so before you start fabricating the structures, extensive simulations was needed. Okay, so plasmons now travel in this profile of very non-uniform carrier density, and that modifies the dispersion. So in an idealized freestanding layer of graphene, you have something like a square root. But this additional periodicity introduces additional bands, and if you zoom at one of these bands, you actually see a gap in this plasmonic dispersion. So then, depending on where your frequency of your light source is, you either have propagating plasmons or not. If you shift the frequency of your light from this band into the gap, you lose this propagated mode character. Then you can recover it if you shift some more. Now, an interesting feature of graphene is that this dispersion can be controlled by backgate voltage. You can shift. It's still square root like, but prefactor in front of the square root depends on the carrier density, and so effectively you shift all this dispersion. If you keep the frequency constant but change the gate voltage, effectively you shift this dispersion with respect to the frequency, and that's what we also implemented in our experiments. So you can start, we start with a regime when the frequency is in the upper plasmonic bands. You see plasmonic waves here. They're not maybe as beautiful as in structures with continuous gates, but they're certainly recognizable. And if we shift the frequency now into the gap, we lose this character. So these waves have disappeared. So you see a darker regions. You see sort of profile behind these regions of separate pillars, but plasmonic waves have disappeared. As plasmonic waves have disappeared, there is a new plasmonic feature that lightens up here at the location of this domain wall between two hexagonal motifs. And if you study the dispersion of this domain wall, you actually see something interesting even in modeling. So now with gray regions, I show upper and lower photonic crystal bands. Then this is the gap everywhere between these bands. But at this domain wall, you start seeing another dispersing mode that is confined to this domain wall only, and that's what we think we observe in these experiments. So photonic crystal feature allows us to control the propagation of these waves on the surface of graphene. And in this experiment, let's see, what we did is we will be launching plasmonic waves with shaped antennas. And we will be gating graphene to different gate voltages. And then it turns out that the propagating character of these modes is actually very different in the upper and bottom photonic crystal bands. So if your frequency is primarily in the upper side, then they travel sort of in the M direction, in the vertical direction here. If you are in the lower band, you send them diagonally. So basically, if plasmon polaritons behave as Bloch quasi-particles, just like ballistic electrons propagate or ballistic phonons in crystals propagate along certain trajectories, you can achieve this property in with plasmon polaritons as well. And this is a little demonstration. Then just by switching the gate voltage on your graphene layer, you can direct these waveguide modes in different directions. And remarkably enough, it's not just in simulations; it works in experiments. Few concluding remarks about Moiré superlattices. Moiré superlattice is obtained by rotating these layers, and these domain walls in Moiré superlattices also act as reflectors of plasmonic polaritonic waves, and you get very elaborate profiles of plasmonic standing waves when they are reflected by this domain walls. And with Misha Fogler, who is my collaborator in all of these experiments, we were able to understand all the subtle details of these patterns. Okay, let me summarize. So this was about plasmon polaritons, or polaritons in van der Waals materials. We discovered a new form of plasmons in van der Waals structures. These are charge transfer plasmons. I later learned that there are charge transfer plasmons in metallic nanoparticles that were introduced by Naomi Halas and her group. So these are, I guess, maybe we should think of another term, but this is the charge transfer mechanism, and so we like to use this term with respect to our structures. In metallic particles, it's a different physics, excitant physics, but different from what we observe here. And then we introduced two polaritonic platforms, Photonic Crystal for platforms for polaritons in graphene. We demonstrated it for plasmon polaritons, but it acts for other types of polaritons as well. I think with these experiments, we have barely scratched the surface of what can be done with nano-optical methods in van der Waals materials. And thank you very much for your attention.
Well, thank you very much, Dmitri, for the awesome talk, for the very beautiful results you presented. Are there other questions on the second part of the talk? We have a first question by Georgi Gordev. You mentioned that with the charge transfer platform, it is possible to get into the visible range. How would you do that?
So, okay, so charge transfer platform is producing interesting properties along across the entire electromagnetic spectrum. Charge transfer platform, there is not enough. Okay, so if the question is specifically about graphene, and I'm kind of maybe need to interpret this question a little bit. So if the question about moving plasmons in graphene into the visible range, no, that's not possible. But there are other charge transfer, so there are plasmons that still don't extend beyond near infrared. But there are, if you use other materials and where charge transfer is very important, for example, excitonic systems, you do change properties in the visible range through this charge transfer mechanism. And certainly in terahertz, there are multiple effects that we are currently investigating. So I think everybody should use this platform because it's so easy and so informative, and you can control the degree of charge transfer by putting maybe your spacer layers. That's also possible. So it's, I think my enthusiastic prediction is that hopefully we'll see more works from different groups on different phenomena enabled by this charge transfer platform.
Other questions? Well, if not, I'll start by reminding everyone that the recordings of the first season of MIDI and are available on our YouTube channel. I wrote the address in the chat, bit.ly/MIDI recordings. The recordings of the second season will be added on the same channel after the second season is finished. If you are interested, please think about subscribing to the channel, because YouTube offers us more services if we have enough people subscribed. This said, I think we can all thank Dmitri again for this very interesting talk, and I thank you for your attention, and I hope to have you with us again next week for the talk by Frank Coppens, who will discuss his works on infrared polaritonic cavities with 2D materials. Thank you again, and see you next week.
Thank you for the invitation.